So my name is Francesco Pase, and today I'm going to present one of our last work. So I'm a PhD student at the University of Padova, and just a few words about myself. So I'm in the final year, and I was a visiting researcher at Imperial College of London, supervised by Professor Dennis Gunduz while working on this project. And in general, my research interests are in the field of information theory and machine learning. But recently, I've been applying these topics to research constraint and federated learning, multi-R bandits, and application to wireless communication optimization problems. As of 1st of June, I'll be a research intern at the Nokia Bell Lab, so I'll be around in Cambridge for the summer. Without further ado, let's go to our work. So as the previous mentioned, so this work has been presented at ICLR 23, and this is a joint work with Barry Van Isik and Saki Weissman from Stanford University, and Dennis Gunduz from the Imperial College London, and my supervisor, Michele Zorzi from the University of Padova. Okay, and basically I'm going to present FedPM, who is basically exploiting sparse random networks for communication efficient federated learning. So it's a pretty new framework to perform very communication efficient federated learning on classification tasks. Okay, so I skipped the usual introductory slide on federated learning. I guess you're familiar with the basics concept of the tool. And let's just say that real-world federated learning consists usually on edge and possibly resource-constrained devices. So, for example, here you can see smartwatches, UAVs, mobile phones, and so on. And there are several issues that we need to take into account while basically designing federated learning frameworks. Of course, the high communication rate needed to convey the nowadays models, the very large models, is one issue. The limited computational capacity of these edge devices is an issue, limited storage capacity of these devices, and as well, there are also other like privacy concerns and, for example, data heterogeneity problems. But with this work, we try to focus mainly on these two issues. So basically, the high communication rate that we need to convey the model back and forth from the devices to the server, and also the large storage requirement that you need to store these huge models into the devices. So just as represented here, you can see there's a different color in a plain vanilla, for example, federated averaging framework. You have 32 bits to represent one confusion of the network or of your model in general. And so you need to communicate all this amount of data every time you set up a new training round. And also to store these models, you need a lot of memory in order to fairly represent basically real coefficients. And the idea is to target these two main issues in federated learning with FedPM. So our task is to compare our framework with other resource constrained state-of-the-art baselines and not to come up with the best model at all. Okay, so our work is built on top of these interesting findings. So basically, this is based on random networks. So the idea, this Ramanujan and colleagues, basically in this work appeared at CVPR 2020, they analyzed the expressiveness also of random networks. So what I mean by this is basically, imagine if you start with a randomly initialized network, and then you keep the weights of the network frozen. And what you want to do is to train the topology of the network. So basically, the idea is to train a binary mask that you can apply on top of these frozen weights, random weights. And the binary mask, basically, when you apply to the weights, it will remove or keep some of the coefficients of the network. And the idea is to optimize this mask in order to have good performance on your data, on your loss function. And so the idea is to optimize the mask to minimize the loss on the data. And they were able to obtain very, very impressive results on classification tasks just by optimizing the topology and not the actual values of the coefficients of the network. So this is kind of some impressive results to me. And the idea is to build on top of this our framework. And specifically, there are many ways to train this binary mask. Of course, this binary mask is difficult to differentiate. So you can come up with some tricks. And one of these is also introduced by Zhu and colleagues in this new other paper. And the idea is to take somehow a stochastic approach. So this is basically what's going on under the hood in the local training phase of within the client devices. So you start from two networks. We have the randomly weighted dense network, that is W init, that you never touch, never optimize. And then there is the trainable, parameter, that's the S of t, that has the same dimensionality and shape of the coefficients of the coefficients vector of the network. And these are real values. So you start from there, and these are the trainable parameters. You apply some sigmoid function to map them into the 0, 1 range, obtaining this theta vector of real values within 0, 1. And for us, these theta values represent the probability of keeping or removing some of the connections. So basically this, you can interpret this as the parameters of Bernoulli random variables. And then you can take sample from this Bernoulli random variables, obtaining some binary mask in 0 and 1. So the Bernoulli samples are parameterized by the theta vector, and you can take sample from this. And once you have a sample, you apply element-wise to the random network, obtaining in the end this W dot, that is basically a randomly weighted sparse network. You take inference, you compute your performance on your loss, and then you can backpropagate the gradient. To backpropagate to the sampling process, we just use the straight-through estimator for the gradient. So this way, you can optimize the trainable parameter, so basically coefficient S, and keep frozen this W in it. What we get in the end is this randomly weighted sparse network that is basically a network whose topology optimized to perform well on the training data, and whose basically initial weights are just random weights. Okay, so this is kind of an overview of the whole picture of the framework. So on the left, you can see what I've just explained, so the local training of this vector theta. And then when you have to basically upload the updates of the model, instead of uploading the score vector S or theta, you just take samples of some network. So basically samples of the M mask, binary mask. And the idea is to just send these binary samples to the server by spending at most 1 bit per coefficient and not more than that, because it's just binary samples. So you can see that each color now represents 1 coefficient, consuming at most 1 bit. And then in the end, the server will aggregate these samples with design kind of Bayesian aggregation strategy that I'm going to explain in a few seconds. And so this way, we can make the whole framework very communication efficient. And also, when you want to store these models, you can start from a random seed. You can recreate pseudo-random, basically, weights of the network that actually are sampled from a binary distribution. So even the random coefficients are kind of binary values. And then you can store just the binary mask in a very efficient way. Okay, so the binary aggregations, basically, the idea is to keep on the server side beta distribution that represent the prior on each parameter. And this beta distribution is parameterized by alpha and beta vectors that parameterize the probability of being active or inactive for each coefficient at each round. And then you observe the evidence, so basically the samples from the clients. And then in the end, you can update your belief with your posterior with a closed-form solution. So we exploit the conjugate properties of beta Bernoulli distributions. And so you simply update the alpha and beta coefficients, and then broadcast the new theta. You can use either a sample, you can use the mean of the beta distributions, or the mode that we observe to be empirically more stable. So that's why we are using this formulation. And with this, we use the Flower framework to build and scale our experiments. And actually, there are other experiments that are coming, and we just send for publication. So this is just a preliminary work. But here you can see basically the performance of FedPM against other baselines methods that are using more or less 1 bit per coefficient in communication round. And so for different models and for different classification tasks like SAFER10, 100, DEMNIST, and EMNIST. And on the second row, you can see the communication rate. So to compute the rate, we apply some arithmetic coding strategy to compress the vector of 0 and 1s, and then we communicate back to the server these values. Of course, as you can see, the communication rate for FedPM depends on the entropy of the empirical distribution of the 0 1s coefficients. So that's why it's not constant, but can change from round to round. And because the network is learning which coefficient you should take and which one you should remove from the network. And sorry, this is for IID results, meaning that the data set is IID split among the clients. And in this case, we have like 10 clients, a very kind of simple situation, but we also have many results with larger models also in the paper. And here you can see this is non-IID split. So basically Cmax means that each client can see at most 2 classes of the data, Cmax 4 and 2, they're 2 heterogeneous setting. Also the size of the local data sets are sampled from some other distributions, so they have a highly unbalanced data set. And you can see here the performance of FedPM against the other state-of-the-art techniques. You can find these and other results also on other scenarios in the original paper. And actually, so in conclusion, I've just presented FedPM, who is a communication and memory efficient federated learning framework. The idea is to outperform state-of-the-art algorithm in the case where you're using more or less 1 bit per coefficient at each training round in order to be very efficient. And we can indeed outperform those state-of-the-art baselines in different scenarios for different models and classification tasks. And the take-home message is that there is a lot of redundancy in the modern deep neural networks, especially the idea is to study where is the information encoded, is it in the topology or in the actual real values of the weights of the networks. Of course, both of them is a combination, but which is the percentage of the topology, percentage maybe of the weights information. So if you want to get access to the full paper, you can follow the link or scan the QR code here. Thank you very much for your attention.
Thanks so much. We have time for a couple of questions. I see one's already jumped up, so that's
Thanks
great.
a lot for the talk. Super interesting. I'm having a few questions, the first of which is how wide were your network layers? Because as far as I know, all this theory that you can prune random networks works only if your network capacity is big enough. So have you trained experiment with different widths?
That's a very good question. Let me just to respond, go to this slide. So this is kind of a representative slide of what you're saying, because here you can see, for example, this is another is a centralized setting where we are getting similar experiments with smaller networks. But for example, here, the idea is to compare the fully dense network against the same network but pruned. Of course, here you can see you compare against the number of parameters. So of course, if you have a large network and you prune it, you have small, basically less parameters. But you can see the performance of the same network when it is fully trained or with all the parameters or not. In our scenario, we're using, for example, ResNet 20, the larger model. And so here the idea is, as you said, you can start from a larger network and then you prune it, but also the weights are just binary weights. So if you compare not just the number of parameters, but the number of bits to represent the network, this plot will be even better in terms of in favor of the random networks. So usually you start from a larger model with respect to the, but our comparison are by, we did the comparison with the baselines by using the same model. So they're using the same model, training the full weights basically, whereas we are just training, the topology of that. Of course, these techniques has not applied that much in like LLM or like language models, or I mean, there are some results, of course, but these are mainly on convolutional networks and classification tasks. So of course, there is a lot of work to do, and it's not clear if it will scale to very large models and to very different scenarios.
May I? Okay.
I just want to see if there's a question online. Is there one? There's a bunch of them just there. No? No? Okay. I will just go with Chad.
So given your Bayesian interpretation or your Bayesian aggregation strategy, it seems that you would get inherent uncertainty quantification associated with that. Did you explore the idea of credible intervals and how well that performed? Because it seems to me that that's kind of an underexplored part of federated learning at the moment.
Yeah, so that's a very good question. So how to exploit this uncertainty information? So indeed, if you see at this, I mean, we actually exploit that in the new paper that we just submitted for a conference, and not in this particular FedPM, but also in other frameworks. So the idea is that even when you want to compare the performance of your model, you can either take a sample, you can take Monte Carlo, for example, So you take many samples, I compute like a distribution of your output, so you have an inserted quantification. So here is not a very Bayesian kind of way of doing that. So we are giving the Bayesian interpretation at the server side, but the network is just a way to train these cores that is stochastic. But yes, you may use that to have many. So the interesting thing is that it's not that variable. So the standard deviation of your performance once you have trained a model is not large. But indeed, you can you can have many, many networks when you sample these masks. And also when you see the distribution of the theta parameter is like a U-shaped distribution, meaning that many of them are basically towards 0, many of them towards 1, indicating which one we want to keep with high confidence. And there are just a few parameters around 0.5. The interesting thing is that if you further do, you can see in the paper, experiments with like 2 maximum number of classes per client and more than 100 clients, so very difficult task. You had low performance, like very low accuracy, but also this distribution is different. You have many weights, many scores around 0.5, meaning that they're not sure about which value they should take, either 1 or 0, because the task is not well basically learned, because it's quite difficult for this model. So I think there are other ways to exploit the fact that you have a distribution and not just real values. And yeah, for example, in this new paper that we have, we are trying to exploit a part of that to further reduce the communication rate into the framework similar to FedPM.
Thank you.
Thank you.